Hello there, welcome back to the Code Athlete. Today I'm going to try from round F in Google Kickstart the festival problem, problem B, which was solved by around 11% of all participants at the time of the competition. Let's see how it goes. Problem states, you have just heard about a wonderful festival that will last for D days, numbered from 1 to D. There will be N attractions at the festival. Each attraction has a happiness rating of HI and will be available from day SI until day EI inclusive. Happiness rating, start day and end day, okay. You plan to choose one of the days to attend the festival. On that day you will choose up to K attractions to ride. Your total happiness will be the sum of happiness ratings of the attractions you choose to ride. Okay, what is the maximum total happiness you could achieve? So I can only choose one day. Okay. T test cases, the first line, that's the 3 integers D, number of days, N the number of attractions, and K number of attractions I choose on my day. Then there are N lines for the N attractions specifying happiness, start and end. Okay. And why is the maximum total happiness you could achieve? Let's look at the examples. Example case 1, the festival lasts 10 days. 4 attractions. I can take 2 of those. You have here a happiness score of 800 from day 2 to 8 and a happiness score from 1500 from day 6 to 9. Oh, and 200 from 4 to 7 and 400 from 3 to 5. So if I choose day 5, for example, I couldn't take this 1500, but I can take all the others, which is just 1400. If I take day 6, for example, I could take the 800, the 1500 and the 200, and I think that's maximum probably 2500. Well, it says only 2300. If you choose to attend the festival on the 6th day, you could ride. Because I only take 2 rides and not 3, so 800 plus 1500. Oh, yes, okay. I forgot about the K restriction. Okay, let's look at the problem sizes. Always important to watch out for those. We want to solve the big data set. We have to take into account that the number of days can be quite large and the number of attractions in 10 test cases. We've done 90 test cases. We have only up to 1000. And K can be also equal to the number of N, basically. Also very large. Okay. So basically we have intervals. And we want to check all the overlapping spaces. So there's probably a way, an algorithm, to find these overlapping spaces quite efficiently, but of course the amount of those I would expect is roughly the size of n. So, or maybe even quadratically. Not quite, because it's like on a linear line. If I have like this interval, and this interval, you could say, okay, these overlap, these overlap, these overlap, and then you get like a complete graph. And then the number of edges would be of course in the order of quadratic, but because it's on a one dimension, there are some restrictions, like if I have an interval here and it overlaps with the upper interval, it also has to go the other way around. If I have an outer interval and this inner interval overlaps with this other interval, then the outer interval also has to overlap. This is interval, so yeah, there are some kind of restrictions. Can we make use of this? I'm actually thinking if it's feasible just to run through the d days and check for every day the available attractions. So if we are at day d, we need to find an algorithm that actually has, like, we need to have some sort of stack, for example, where we push down all the currently available attractions and remove those that are not available anymore because they stopped. Because then we could look up in linear time of only the available attractions. But I mean, this list could potentially for every day become as large as n. So I can tell you that the runtime of n times d, just from the amount of elements we have, is roughly 9.10 to the power of 10, which is too big. We can't run this in a small enough time. So we would need to find something in the order of, because d times constant, that would be something we could totally do, even with a large constant. It would be okay. So that's what I'm currently thinking about. If we can find an algorithm run in that time. What am I thinking? I think the method I just outlined with having like a stack of, we could have a dictionary lookup where we say, we're getting from day d to day d plus 1. And then we can have a dictionary where we write in all our n attractions, and in this dictionary, like, there would be two dictionaries, a start dictionary and an end dictionary. And we could look in the start dictionary for this day d plus 1 and get a list of all the attractions which start at this day and add them to our stack. So this is basically our stack of attractions. And we could update this using these two dictionary lookups, hashmap lookups. Because then we would also use the end dictionary and look which attractions stop at day d plus 1 and update our attractions accordingly. This would be probably a set, not a stack actually, maybe a set of attractions. because it's easier to remove in an unordered set these attractions. Not quite sure yet. I think there should be a good data structure for this. Yes. But I mean, potentially this list, the update and operations are okay, because they're not in the order of n times d, but because every attraction has only one day at which it starts and one day at which it stops, so the amount of update operations over all days is just 2 times n, and not d times n. So we couldn't have at every day n attractions that start and n attractions that stop. So this would be okay, the update operations, I think. So basically we would then have an algorithm of the order d plus n now, which could give us this. But the problem is now, I think, how do I make use of this set of attractions? Because this could potentially be a size n for every day. And I'm now thinking, what is if because now I have to find the top k, because k is only from this list, we can only visit k attractions. Find the k largest happiness values in this set. And I can't do this every day for new. Like if this is size n and I look for the top k and the next day I do it again, then I'm again in this n times d runtime. So maybe I need another structure on top of this structure, which keeps the set kind of ordered in the happiness values. And maybe also keeps the sum up to date, because k can be also as large as n, and I can't sum up k values every day. So it does not help me if I have it sorted, if I still have to add them up every day. So I also need to keep like the sum for every day. And during the update step, I need to check if something is removed from top k. And if something is added to the top k. And I think this kind of works, because if I have an ordered set, ordered with respect to my happiness values, the deletion and insertion of a new happiness value basically costs me only a log, because I need to make a binary search for the position and then I need to insert or remove. And binary search is the size of log n. So I think we could get something like this from the runtime complexity, and that should be fast enough, because log n is very small. Like this would be in the range of the small values we can put in here. So I guess the set of attractions is basically a multi-list. And every time I remove an attraction from my top k, I need to remove the happiness from my total score and then add the happiness of my newest kth element, which I can check afterwards, I guess. The only thing I'm now wondering is that like this ordered set would be more like an underlying list structure. If I want to find the kth element, I need to always start at the top of the list. Or for example, does a multi-set Yeah, so is a multiset a thing that I could use? I need to actually, I use not enough C++. Multimap, is it called multimap? I think so. Yes. Yeah, so this is basically my problem. I cannot access elements by the absolute position, which I would need in order to access the kth element after removing something of my top k. So this multimap is not good enough. Can I construct my own data type which tracks all the information I need? Probably not, right? Otherwise it would be some standard data type. I'm afraid that I have to use something about the intervals. There's some structure because we're using intervals. I mean, there are many possibilities how you could go about this problem. For example, another thing would be to check the kth largest attractions of the n attractions you have and look for the overlap of them. Or, going about it like greedy, starting with the most valuable attraction, checking its interval, overlapping it with the next largest attraction. Yeah, probably like in a worst case, those two don't even have an intersection and are very close in happiness, or maybe even have the same happiness value. Then you need to bifurcate, like one of the two is probably a candidate for the one day you want to come. So you have to check for the first day all possibilities and for the second day all possibilities. That seems like combinatorical explosion and not feasible. Yeah, that seems totally not feasible. I think my idea is quite close to a working solution. I just don't see how I could update this top k value. I can easily update the stack or the set, or even the ordered set of attractions. Okay, what is if I have in my multi-set a pointer to the kth largest value? And now, if I add a value, I can just compare it to this kth largest value, and I know if I add it on top or below it, and based on that, I can move my pointer around. That seems like something that should work, actually. Okay, I think that might just be the solution, just having a pointer. I think I will try this. Let's switch. I think I will write my own class because I'm actually not too sure how we'll use that here. So here's my template code. You see here the link, but it's also in the description below. I also made a video to my template in case you want to use it for Kickstart or Google Code Jam competitions. But you can also use it for any other competition with a few modifications, but it's optimized for those. And the communication type is integer, long, it's my abbreviation. Don't have a default value mode on, no interactive problem, so this should all be fine. Let's read the inputs. These are the first values. And then we have the attractions. Yeah, let's do it like this. Now we pretty surely need the dictionaries, which I spoke of earlier, adding and removing our attractions. So yeah, it's a dictionary where the key is the start date or the end date, and the values is basically a list of IDs, attraction IDs. So starts and ends. Correct abbreviation I use here. And we can actually put this here. Starts from I, pushback index I. Okay. And now we need the data class with our stack basically and the top k value. We don't really need a class. I can maybe write just an update function and some variables that have the current stack data. I will do that, I guess. Void insert. Don't know if that name clashes with anything actually. And void remove. And I will guess the first thing we will have there is the thing we want to insert or remove. It's probably just the index of the attraction. I just remembered, because the end dates are actually inclusive, we will put the end dates here at +1. And also because they are all 1 base, we actually will decrease them by 1 before we do further processing. This +1 means now it's exclusive in my ends dictionary. And actually, let's just put also the end E list exclusive, like this. And that means if I check if we're at day D, small d, and something is in the ends list, then we remove it, which means it basically finished at the day before. Yeah, that makes sense, I guess. I hope to you too. Yes, so we insert the index attraction. Let's call it attraction. And the first thing I think we also need is a reference to top K sum. It needs to be updated. And the rest is all the stuff we need to keep track of just to make the insert and remove operations possible. So I will add this later. So the result will be 0 in the beginning because I hope all the happiness values are actually greater than 1. Okay. Then we will iterate over our dataset D. And we will have a per top K sum value. We will set that to 0 as well. Now we will have a look at all the starts and ends. I hope actually that the end date is always bigger than the start date or something. Oh, I guess something can end at the same date as it starts. Yes. But is it actually written that it's a condition? Oh, yes, here. Sorry. Okay. So we don't have to check for that. Yes. For each fraction in starts at day D, we insert the attraction. I think we need to dereference it. And we update the per top K sum. We will do the same with the attractions that end at this day, but those need to be removed from our stack. And then we just take the maximum over all days. Sorry, so maximum of our current result we have and the new top K sum we have. Now a small trick I already thought of while I spoke about my solution is probably that all the stack values I will put here into the function calls. I will insert K values with 0 artificially so that we will also always have these K attractions and that the stack will basically never have less than K values, so the current top K sum doesn't have these boundary conditions where maybe if I have like in the beginning, for example, otherwise the stack would be empty, so the current top K sum is, I don't know, the pointer wouldn't be defined, right? We talked about the pointer, which always points at the kth position. And yes, that pointer would be broken, I guess, if there are not K elements. Okay, so what kind of data do we need? I think we need a list. of the values. Oh, I just thought of that in the list I actually can't do a very good job at binary search, which might be a problem. So the happiness values actually also can't get larger than 3 times 10 to the power of 5, so maybe I make a static array. Actually, I will do that, yes. And this will be the stack variable. Yes, I think that's a great idea. No, not great, but it will work in this case. And for every happiness index, basically, we have a list of attraction indices. No, probably a set of attraction indices. Actually, just a counter of how many attractions with this happiness value is enough, right? Because with the attraction index I get in the insert call, I can just look up the happiness value and then I can say, okay, from this happiness value we have now one less. Yeah, that's totally enough. That is actually great. So now let's put in the size there. 3 times 1.5 plus 1. We initialize all of them with 0, so we have 0 of them, but now the 0 happiness value we have from those, we have actually k. So that the kth pointer is defined. Yes. So let's plug in the function calls the stack actually. And the pointer, now the pointer needs basically a happiness value and inside this happiness value a position, because if I have for a happiness value 10 attractions, I need to know if the top kth attraction is basically the third of those 10 or the fifth of those 10. Let me shortly draw this actually. So let's say here's my stack. What different color? Stack with my happiness values and my number of attractions. Number of attractions. And yes, let's say for happiness value we have our k equals 3, small example. This is the thing I initialized. There are no attractions actually with the happiness value of 0. They all start at 1. So this will never change. And then with happiness 1, 2, 3, we have here like 1, 2, 1. So yeah, and the pointer would point in this case to the second value here in this 2 position, because the top 3 are this 1, 3 and 2 of those 2's. Now if I would insert a position at this 3, so if this 1 gets a 2, then the top k position would basically still be at the happiness level of 2, but I would only take 1 of those 2 2's into my top k selection, because I have 2 3's now and would only take 1 2 from here. So I need to describe my pointer by 2 numbers. The happiness value and how many of those happiness value attractions I will actually take. So I will have a happiness pointer and a pointer number. of happiness. So the pointer for happiness is of course 0, because in the beginning we have only 0 happiness values, and the pointer number of happiness values we take is k. And we also have k in the stack, but I'm not even sure if that's important at this point. And yes, let's add to these calls those pointers. Seems to make yes. The for each doesn't return iterator, so I don't actually have to dereference this. Sorry for that. Bit rusty on my C++ skills. But I think now we can implement this. And then we're actually finished. Yeah, very, very interesting problem actually. Let's hope that this works. So the insertion operation. First we take the happiness value of our attraction. Then we will check if this happiness is actually higher or lower than our happiness pointer. If the happiness is higher than the pointer happiness, then we will insert it on top. That means, first of all, I should maybe say stack at the h position has one element more. Now, if the h at the pointer position is bigger, we need to update our top k-sum. Because now we can use this h, but we cannot use one of those pointer hi values anymore. So going back to this table here, basically when we move from we're having just one happiness value of 3 to 2, then we can use 2 of those and just 1 of those, but our total sum is just gaining 1 and not 3, for example, because we are switching out basically 1 3 for 1 2, so the difference is the only thing we get for our top k sum. Then also we have to say that the pointer number is now actually decreasing by 1, because we're using one of the higher h levels. And this decrease could actually mean that the pointer number is dropping to 0, so we should then change probably the pointer HP to the next higher number. Now I'm actually thinking, whoops. At this point it wasn't a very good strategy to have you know what, I think I will actually have an ordered set of values that is available. Insert a 0, that's something we will always have available. Yeah, so because we need to make this check, if pointer number is equal to 0, we need to modify the pointer for happiness to the next higher happiness value. And there's probably an operation. Because right now I'm thinking we could actually get away with an algorithm with a runtime of just d and not d times log n. But no, we need to insert, actually. We need to insert h here as well. And now we need to make a call to the C++ reference for set and check how we get the next higher number. Because there's something for that, I'm sure. I think it's something like find, getting an iterator and increasing that iterator by 1. Yes. So pointer avail hap equals avail hap dot find pointer happiness. Now this is a pointer. We can increase that one. And then we set the pointer happiness to the next available happiness, and the pointer number is now all of the attractions at that happiness level. Actually, is this updating really that variable? I hope so. In Python, that wouldn't be the case, I think, because integers are atomic. I'm programming a lot in Python, but I think in C++ it should be okay. Yeah, I'm pretty sure it should be fine. Yeah, but in the case the pointer number was actually higher than 1 and we decreased it here, we're still fine with these two values, pointer happiness and pointer number. So I think this case is handled. In the other case it should be simpler because we updated the stack, but we don't need to update the top case sum and also not the pointer because we inserted our happiness value below this. Yes, so we don't even need an else clause. So here we remove it and we can again get our happiness level. Actually, I'm just realizing we didn't even need to have this attraction index here because we're just using happiness value. Here the same, but it's fine. In here. Now we decrease the stack from h by 1, and now the available happiness, you would say, okay, let's remove h, but this we only need to do if the stack actually got empty at that position. Right? Because otherwise it means we still have something left. The available happiness doesn't count multiples. If we insert multiples at the same time, it basically just says one insertion. We should really only remove it if we have not any more of those. I think I'm basically constructing a multiset here myself. So yeah, I guess that's a bit silly from me, but I'm not too not well read on multi-sets and multi-hash maps. So yeah, I will stick to this. And now if, again, this h value was smaller than the pointer of happiness, then basically we didn't change anything in the top case. So we only need to, again, consider the case okay, there are I think two cases now. Because if h is equal to the pointer of happiness, and the pointer of number is smaller than the elements we have available, then it should be also not mattering. But if, so there's a special case when h is each equal. I think we will handle this later. So let's first do this case, and let's do an else if h equals pointer equals. Just to keep in mind that there's a special case. But if it's lower, again, we're not changing anything in the top k configuration. We don't need to update anything. If h is bigger, then we definitely need to update something. Because we're losing that h. Oh, we need to actually first find the next happiness pointer, the new happiness pointer. So if if the stack at the pointer of happiness is smaller than the pointer of number, that means we can take one of those happiness into the new top k selection. Sorry, if the stack has more than the number of elements we selected. And that's fine. Else, in this case, the pointer number must be equal, because it can never be bigger than this one, hopefully, if the algorithm is correct. So in the else case, they are actually the same size. Let's actually just write a small assertion for this. Now, where was my train of thought? I think we wanted to, if it's the same, we need to find basically the next lower happiness pointer and choose the first element of that to add. So in that case, top k sum would also be pointer hit points minus h. Pointer number would be set to 1. And first we need to find pointer of available happiness. Plus plus, gives us the higher pointer, but we need the lower pointer. I hope it's in bidirectional iterator. Because now we need to degrade our happiness value basically. So we take the smaller happiness value. So that's what we set our new happiness pointer to. When we do the updates, is it erase? Those cases should be fine. We updated the stack, we updated the available happiness, the pointer points we don't update in this case, which is correct, and we updated it in this case, and the pointer number was also updated. Now we have the special case where the happiness is equals to the pointer hit points. And we just decreased our stack at that position. Now, if the pointer number is smaller or equal to the stack at that position, H or PTA happiness is the same, then we're actually fine, I think. Because then we have still enough in the stack of attractions at this happiness level that we can choose our top K from this, and we don't have to change anything. So actually we just have to look at the case where the pointer number got bigger now. So it's probably should be exactly bigger by 1 in this case. Actually, let's check that. And in this case, you're basically doing the same as in this case here, I would say. Finding the pointer to the current happiness, and now I'm realizing if there is a 0 at the stack position, we actually already erased this. So maybe we should... Here there's no conflicts, because here we are looking for pointer hint point where this is unequals to H. But I'm thinking we should probably put this in the end, so that we can still find this happiness value in the next higher, or in this case, the next lower happiness value. Yes, so we're basically doing the same in this case, yes. That makes sense, I guess. And I'm thinking this should be it, actually. I think we should have finished. Oops. I almost forget what I'm doing there. Edit requirements. And let's check if this works. Oh! It seemed to work instantly, actually. Interesting. So I guess we'll load this up. Yeah, so very interesting problem. I really think now that I should have used multi-sets in this instance. Let me just check if they actually exist. Multiset is. So then this whole insertion with the check here would have been probably not necessary. And I could probably use it also instead of the stack, so I would have had the stack with a double meaning basically, where I could count the number of elements, yes. So that is basically the merge of the stack and the available happiness mechanism into one thing. I'm not sure how is there an iterator, how that would work? Maybe this would also have all this logic inside it. That would have been very interesting if that would have been possible. Let's check what the find function does. So I think it wouldn't have done that actually. Yeah, but I'm not quite sure if I have an iterator on this, then I would have added one. Yeah, I'm not sure if it would have done that. So yes, but our solution worked. Nice. So I hope this was kind of interesting for you, rebuilding basically a multiset from a normal set and a vector structure. I think internally that's pretty much the stuff that should happen. Plus, of course, I built in this second counter, having a good iteration structure over my multiset elements, which I think wasn't supported by the multiset standard library, but I could be wrong. If so, if you know better, please write in the comments, and then in this case I'm very sorry that it took me so long. Yes, but if you felt the explanations helped a bit and you understood a bit and found this problem interesting, feel free to leave a nice comment or a thumbs up, or even ring the bell for future videos. I might do this more often now. And I hope to see you soon in the next video.